So in the last video, we talked about Euler's formula, and then we showed the expressions for how to extract a cosine and a sine from Euler's formula. And we have a powerful set of expressions there for relating exponentials to sine waves. And so now I want to show you an example, just a preview of when we get to the formal AC analysis, how are we going to exploit these expressions? How are we going to exploit these formulas? This is a real-world signal. This cosine term, let's suppose we build something that has a cosine to it. That could be something like a microphone that's hearing sounds that look like sine waves, and we would model those sine waves as a cosine wave, and they come into some electronic system. So let me draw a sketch of the clever approach that we're going to use. So what I'm going to do is I'm going to build, here's a circuit I'm imagining. There's resistors, and there's capacitors, and there's inductors, linear elements, and we can have sources and stuff like that. So there's something in here, and we have something going in and something coming out. Okay, voltages and currents coming out, voltage and current coming in. So I'm going to drive my circuit with some sort of sinusoid. I'll call that sinusoid, I'll give it an amplitude, and I'll call it cosine of omega t. And omega is the frequency, t is time, a is the amplitude of the signal coming in here. Now, that signal is going to go into this circuit here. Something's going to happen, and there's going to be a voltage coming out of here. So we'll get V out over here of some sort, and it's going to be some amplitude, and it's going to be some sort of a cosine wave of omega t plus some phase angle, some angle. That's our job to discover this. That's the circuit analysis problem for AC analysis. We put in an AC signal. We're going to get out another AC signal. This is the forced response. Remember, it's going to look like the input. It's going to be at the same frequency, but it's going to be at some different phase angle. So in order to do this, there's a fair amount of hard trigonometry we have to do. There's going to be a lot of cosines and sines and angles and things inside this. So that's pretty challenging analysis. Now, what we do with Euler's formula is we turn it into exponentials, and we already know how to solve exponentials. So we take the same circuit. It has the same stuff inside it as resistors and capacitors, the same exact circuit. Let's draw the same exact circuit there. That's identical. And it has the same outputs, output port right here. And this time what we're going to do is we're going to basically take this cosine and we're going to make up in our head, we're going to cast this into an exponential. And the way we do that is we use that formula. We use Euler's formula. And we basically create two sources, two separate sources, and they're exponential sources. This is going to be a over 2 e to the j omega t. That's this source here. And this source here is a over 2 e to the minus j omega t. That's this waveform. And if I add those together, like that, now remember the equation we just looked at, Euler's formula, says that cosine equals that. The voltage here is exactly the same. And all we've done is describe the same exact cosine waveform as these two imaginary exponentials. Now, I can't actually, on my workbench, build one of these things. These don't exist in real life, but they can exist mathematically. They can exist in my head. And I know that if I add these two voltages together, that I do get a cosine. So in our heads and on paper, we can actually drive circuits with these things. We can't actually build it, but on paper, we can do it. And now that I have two sources, I can use the principle of superposition. This is another use of the very powerful idea of superposition. So using the idea of superposition, I'm going to apply each of these two inputs one at a time and then add the results together. So over here, I'm going to get two outputs. I'm going to get a V out 1. Let's call it a V out plus, which is what happens when I put in this plus source and I suppress this one, which means I short it out. I'm going to get a V out plus. And how do you solve a differential equation when you have a exponential going in? Well, we know this. It's going to be an exponential answer. It's going to be some constant times e to the j omega t plus some angle. And then I'm going to solve it again. I'm going to add to that v out minus, and I do that by suppressing this input and turning this one back on using superposition. And v out for the plus, v out for this source here is going to equal some other k. Let's call that k plus and k minus. E to the minus j omega t plus phi. So I'm going to put in two exponentials. I'm sure I'm going to get out two exponentials. And now, using Euler's formula, we know how to combine these. We can use that same expression and we can recover our cosine. We can recover the real signal. And this will have some magnitude b. We don't know the magnitudes yet, but we know what the shape of the waveform is. And if we look at this is the same thing as this here. And we did it by decomposing our cosine into exponentials, putting each exponential through this, and then recombining to get cosine. And we do all those steps because solving differential equations with exponentials is the easiest way to do it. So just that you know it's not twice as much work, what's going to happen is going to turn out that this whole solution down here using the negative exponential, the answer is going to be exactly the same as the positive exponential, except for there's just this conjugate, this complex conjugate in here. So for real signals going in, the answer goes through, and it's always, these answers are always complex conjugates of each other as long as we start with a real input. Okay, so that was a review of Euler's equation and a little sneak preview of how we're going to do AC analysis using this really powerful tool.